Hi, I'm Antonio Sala, and in this video we are going to compute realizations of a Gaussian process with a given covariance kernel, autocovariance, given some observations of it. So our problem statement can be conceptually understood as having a range of abscisses, which will be from -2 to +3. And then our Gaussian process is a random function, so that we may have a prior on how smooth and what's the mean of these functions and some confidence intervals, let's say. We did that in a prior video. But now, even if we have that prior, let us imagine that that Gaussian process is the velocity of a car in some points of a motorway. Say 0, maybe some intersection or particular speed camera, let's say. And well, we wish to study or model how drivers brake or accelerate or whatever in the vicinity of my speed camera. So we have that prior, but in this case, we have done an actual experiment and we have observed that at these 3 positions in the motorway, we have hidden speed cameras there or some instrument on the tarmac, and we measured these 3 velocities. So given our prior on how quickly or not drivers modify their velocity, then we wish to obtain, say, a confidence interval on which will be the most likely speed values our driver might have. And we also wish to obtain, for, let's say, further study or simulations, some possible trajectories consistent with the measurements. So formally doing that and examining the Matlab code needed is the objective of this video. So everything started with a prior covariance kernel or autocovariance function, the covariance between speeds of the cars at kilometer x1 or x2 in the motorway. This loop to compute the covariance for all pairs of points if x1 and x2 were multiple motorway positions. And in a previous video to this one, we discussed that in some test points, 250 of them, we could plot this mean function and these confidence intervals. Oops, it was 200 points, and with that mean and that covariance matrix, we could throw the dice to get some realizations of the prior assumptions on my random processes. So this would be some likely speed trajectories of my cars in the motorway. You know, they brake when approaching the speed camera and they accelerate afterwards. And well, these random fluctuations are assumed likely for me given my prior covariance. But now, if I have some data, if I measured this particular speed at these points, I wish to do the equivalent thing, but with the random realizations passing through my measurements. So now we need to review the formulas for the best prediction in mean and variance, which will be implemented in this code. So let's do a brief review. In this theoretical review, we will understand as A, the variable I wish to predict, and B, the variable I did measure, the information. And I assume that there is some covariance, some statistical correlation between A and B, so I can use B to predict A, and indeed, it's a famous, well-known formula that the best prediction of A given information B has a posterior mean given by the prior mean of A plus some gain multiplied by the increments of measurements B above the mean, and this gain is covariance between the predicted variable and the information variable times the inverse of the variance and covariance matrix of the information. And the posterior has this mean and this variance, which is the prior variance of the variable I wish to predict without data minus the variance decrease that information provides to me, which is covariance times inverse of the information variance times covariance transposed. Well, these are well-known formulas. And then we will just apply these formulas when A, the variable to predict, is the value of the stochastic process at some points x1, and B, the variable I have information of, are the values of the function at some horizontal x points. So I will be able to incorporate these measurements to get a posterior prediction. Well, in my code, I compute the prior variance and the prior mean, and this is the covariance between the variable I wish to predict and the variable I have information. I wish to predict velocity at x1, and I have information of velocity at data.x. This is the covariance of the information, but if my information has some measurement noise of variance lambda, then I add that measurement noise to the diagonal of the covariance, so my information variance is increased. That means white measurement noise, let's say, and then covariance times the inverse distribution in Matlab syntax of this noisy information gives me the gain in this formula here, and that gain times the increment of the information with respect to the mean gives me the increment that I add to the prior mean to get the posterior mean. And then this line of code here is how to encode this variance equation here. And the last line is just in case some round-off error make my variance non-symmetric, then I tweak it a bit to make sure it's symmetric, but that line has no conceptual statistical meaning. So with this prediction, this means that if I assume that I measured at these points in the motorway these three values, 0.81 and 0.25 of the car speed, then with this predict GP function I just discussed, I can obtain the posterior mean and posterior covariance matrix, 200 by 200, and the posterior mean, of course, 200 mean values. And then with this line I can plot the posterior mean and confidence intervals with the plots you see below. And so here we have in black and pink the prior mean and confidence intervals. We have the black asterisks indicating the measurements, and then we have the posterior mean in blue and the posterior confidence intervals in solid red. And you can see that as our measurements had some measurement noise, I still have some remaining uncertainty on which is the precise value of my velocity, because I had measurement noise. If the measurement noise had been 0, then the upper and lower confidence interval would have touched at the measured points, but this is not the case. So this is the best prediction in mean and variance of the posterior, given my observations of the car's speed. This one will get a fine, possibly, because this car accelerated when reaching the speed camera. Of course, that posterior is not stationary because the variance and, of course, covariance depends on the horizontal position. And, of course, you can see that in the covariance, these points separated 5 samples, let's say 10 and 15 is the number of samples in this, not the separation in distance, but they are evenly spaced. So these points separated by 5 test points have 0.2 covariance, but these have 0.16, and so this is not stationary. Once I have measurements, and I can plot the standard deviation before and after having data. So with no data, standard deviation was 0.6, and at the points I have measurements, then my knowledge on which was the speed is much higher, much lower standard deviation, up to measurement noise precision, of course. The farther away I am from a measurement point, the more uncertain my posterior estimation is. And if I am farther away than, let's say, the correlation distance, then the velocity at kilometer 3, let's say, is statistically independent from the velocity at kilometer 1.4. This is the posterior, and now with the multivariable normal random function, with this mean, posterior mean, and with this posterior covariance matrix, I can make some trials and draw some samples of likely speeds of the car. This is just cosmetic. You can pause the video or download the code and analyze it, just plotting stuff. And the important thing is here. Here we have, in greenish lines, let's say, some sample realizations. In black I have the measurements and the mean. In red the confidence interval, and so these sample realizations, well, have the smoothness, let's say, of my prior covariance power spectral density, which I assumed in my code, and they pass through the measurements, well, up to a given, uncertainty, because I had measurement noise, so my simulation somehow builds smoother curves according to the prior that do not exactly pass through the measurements because they were noisy. I can repeat and get some other realizations. So you can download and look at as many samples as you wish. And if we wish to understand the meaning of correlation distance, if we think that the correlation distance is 10 times smaller, well, then the interval in which measurements are useful to predict velocities at other points gets much narrower, 10 times narrower. So a measurement here is useless to predict velocities here or there. And of course, if correlation distance is 10 times narrower in space in this motorway, then power spectral density is 10 times wider. Things move up and down 10 times faster with 10 times more frequency, 10 times more bandwidth than the other simulation. On the other hand, if my correlation distance is very big, then that means that my velocity profiles are very smooth. So in this case, this is the posterior confidence interval between the red things. It must be very smooth, and you see that the measurements are outside the confidence interval, which means that my underlying statistical model thinks that it is very, very, very unlikely, having had this quickly varying speed, if my prior is so smooth. So somehow I have an issue with the modeling. Either the measurement noise is much larger than I thought, or the smoothness, the power spectral density, is wrong and my prior is too smooth given my actual samples. But okay, model validation issues are out of the scope of this video, so going back to the simulation parameters I started with and just superimposing 400 simulations, we summarize the video saying that, okay, in this video we computed the posterior to having some observations of my Gaussian process, so we compute the mean and confidence intervals given those observations, and with the full covariance matrix we sample some realizations of those possible velocity profiles in this motorway that, of course, 95% of them were inside the confidence interval. So in this 400 will be like 20 of the lines should be outside the red limits. And we also inspected the effect of varying the correlation distance in the covariance kernel. So we finish here. Thanks for watching.